Good day, everyone. I'm Joe Ferrara, and I will be hosting this webinar today. 3D-ED in pharmaceutical compounds, can we measure everything? Presented by Dr. Jordi Bennett-Buchholz. Jordi is a crystallographer. He received his bachelor degree in chemistry in 1995 from the University of Duisburg-Essen. He received his PhD under the guidance of Professor Dr. Roland Boise in 1988. Then he did an 8-month stint as an invited researcher at the University of Berkeley, University of California, Berkeley, under the guidance of Professor KPC Volhart. In 1998, he started as the director of the crystallography laboratory at the Central Analytical Research Department at Bayer AG in Germany. In 2004, he joined academia, became the laboratory manager of the X-ray diffraction unit at the Catalan Institute of Chemical Research in Catalonia, ICIQ. Additionally, since 2005, he has been the scientific advisor of the technological platform CRISPHorma, which collaborates with pharmaceutical companies in the study of the solid state of pharmaceutical compounds. He has 270 papers to his name, 27 patents, and has an H-index of 53. Before I turn the floor over to Jordi, I will go over some housekeeping rules. To start, a recording of this webinar will be made available. After the webinar is complete, you'll receive an email with a corresponding link to view the webinar. You can also check out past webinars at www.rigaku.com, webinars past. You can send us questions during the presentation. Questions will be answered at the end of the presentation, not during. Please use the Q&A button to ask questions. This will allow us to keep track of them and to see how they're being upweighted. Use the chat only for technical problems. For example, if audio drops out, use the chat. Do not use the chat for questions. We will not monitor the questions there. If you're a customer and you haven't already joined Rigaku Forum, please do so. The link is shown here. You can also scan the QR code on the right side of the screen and subscribe to your favorite topics. And without further ado, I will turn the floor over to Jordi. Jordi, you can start sharing.
Okay, thanks and for the nice introduction. And I will try to start sharing. Let's see. This is the right one. So can you see properly my presentation?
I can see your presentation.
Okay. Okay, then thank you very much and hello to everybody. So I will tell you my story about 3D-ED since our COVID side and show you a few examples how we deal with pharmaceutical compounds and using electron diffraction. First of all, let me see. Why can I not? Okay. Just tell you that I am at the Catalan Institute of Chemical Research. This is in Tarragona. Tarragona is very close to Barcelona, and we are here around 350 people working in catalysis and renewable energies and doing different fields of research. Myself, I'm leading one of the characterization technologies department in concrete diffraction unit. It was called X-ray diffraction unit, but we have to change this now. It's diffraction unit. There, I am leading a lab which is having 5, let's say, diffraction devices, 2 single crystal devices, 2 power diffraction devices, and now newly 1 electron diffraction device. The lab I am sharing with Marta Martinez, which is helping me doing all these characterizations and analysis. And we have also an area of sample preparation and sample crystallization. The fields where we are, I don't know, If you could please change the page now. Okay. We are doing generally solid state research in single crystal X-ray diffraction, powder diffraction, and crystallization. And also, as you will see, I am scientific advisor of a unit called Crystallama, which does research in the field of pharmaceutical compounds and its solid state. The areas where we work can vary from crystallization and preparation and structure solution of highly sensitive reaction intermediates, preparation of single crystals of small amounts of samples, and manipulation also of small single crystals for X-rays down to 5 microns. We try to crystallize difficult to crystallize substances. We also make especially focus on the determination of absolute structure and the absolute configuration of pharmaceutical compounds using molybdenum and copper radiation. And also we do charge density studies. We do also studies with variable humidity and temperature using powder diffraction. And we do also other works related to quantification and limit of detection in crystalline phases. My story started during the lockdown in 2020, where I set as a goal that we would like to have electron diffraction system, and where we would like to characterize the structure of nanocrystalline materials. We expected at this time to be able to measure different types of products like drugs, natural products, pigments, zeolites, up to minerals and proteins, coughs, moths. And the idea behind this story was to create a national service available for the scientific community. So that during the lockdown, I started to learn and to join all the possible things related to electron diffraction. As antecedents, I had 3 important things. So the first was that in the last years, let's say, 3D-ED was starting to run. No? They introduced new protocols for acquisition of data. And also in a second point, they started a new approach, which was continuous data collection and the use of shuttleless detectors. And to this came that in 2021, 2 companies brought to the market, let's say, dedicated electron diffractometers, which were the companies Rigaku and Jordi. So that we set a long-term game, which was to develop the technique of electron diffraction and make it accessible to the scientific community, with one condition: we have to maintain, let's say, the maintenance of the equipment should be financed by the users. By the other side, ICIQ, my institute, should provide for the place to install the device, and the diffraction unit should take care of operating and running and getting new expertise on this device. So that after applying for a grant, we were having a very positive response. And so we got close to 1.5 million euros to buy this device. And so we tested the first devices from November 2021 to June 2022. We had an open tender in July 2022, and which was awarded to Rigaku Corporation, so that finally in May 2023 we installed our Synergy-ED system here at our institute. And now I changed a bit the topic. So I am an X-ray diffraction expert. I'm a crystallographer, no idea about microscopes, so that I tried to learn from my point of view how this runs and what it does. And so the basic principle is that, in fact, single crystal X-ray diffraction and electron diffraction are quite similar. So X-rays diffract in electron densities of atoms and molecules. Electrons diffract in the electrostatic potential of atoms and molecules. And in a measurement, reflections based on the diffraction of electrons in matter are collected, and the data are processed very, very similar to X-rays. But now, of course, a but comes, no? But we have a very strong interaction of electron radiation with matter, and we see also that measurements are performed under vacuum. So that we have following consequences. Electron diffraction is dynamic. We have strong radiation damage in some cases. We have also vacuum damage, and the dispersion atoms or dispersion factors are dependent on the atom charge. Evaluating these, I see that in fact, electron diffraction is an effect in which primary reflections diffract again in the crystal lattice. So we get, let's say, a secondary reflections which propagate through the crystal. This results in a quite complex diffraction pattern where there are, let's say, overlapping reflections of the different orders of this, let's say, diffraction. And the consequences are that we have this dynamic data, what we call, which cannot be scaled and is strongly dependent on a crystal size. In some cases, due to this, let's say, modified intensities, it's difficult to determine the unit cell and the space group. And when we use, let's say, the classic refinement, kinematic refinements, we get very, very bad statistics. So we get very high R values, which are at the beginning, they were like, wow, what is this? So high values, but they seem to be normal when we are using electron diffraction. And radiation damage is also an important issue with electron diffraction. And so in some cases, when we have interaction, when we have diffraction with electrons, the samples are quickly destroyed, sometimes in few seconds. And it seems, or we have the feeling, or I have the feeling, that especially hydrates and large organic molecules with hydrogen bonds tend to be more sensitive to damage. But I already have a solution. So one way to avoid these problems is to join several measurements and then refine them together kinematically to merge the data. The only problem is that in this case, you cannot use dynamical refinements. You cannot merge data before scaling. And another way to save light or to increase the time of reflection, you should cool, or you can cool the crystals. Then in relation to vacuum damage, so especially by pharmaceuticals, where you have hydrates or solvates, or let's say molecules which are quite volatile, they would be destroyed quite quickly in vacuum. But we can prevent this just freezing these crystals before introducing them into the vacuum chamber and cooling them down before introducing them to 100 Kelvin. And then we can measure in a strategy where we make, let's say, rotation in phi in a range. This is a bit exaggerated, let's say, from 60, -60 to +60, or -70 to +70, and make a collection in continuous rotation. And we can take images in the steps from 0.1 to 2 degrees. And this in total can take less than a minute if we are having some diffraction in the crystal. So this means that although the crystals are quickly destroyed, we can also measure very, very quickly so that we are able always to get some data from the crystals before they destroy. And finally, just to comment that we have interactions between radiation and matter, so that due to the charge of electrons, if we have cations, anions, or different charges in the atoms, we have different, let's say, higher or weaker dispersion factors. And now going to the point. So which advantages, in my opinion, has electron diffraction? So of course, the measurement of crystals in a nanometer range. We can also use extremely small amounts of samples, so we need just nanograms to be able to perform a measurement. We can do fast single crystal measurements, as I said, in a range of a minute or less. We have really, in a standard case, easy crystal preparation. And I see also as an advantage the dynamical effects. As disadvantages, I see a possible rapid destruction of the crystals by electron radiation, that samples are measured under vacuum, and also a disadvantage are the dynamical effects. So you see they are in both positions, and I will explain why they are in both positions in the next slides. So then one of my points, we want to measure all different types of samples, but now I will focus on pharmaceutical compounds. I took, or I had some questions to be, let's say, answered when I started testing. So one question was, is going to be vacuum hindering the measurement of part of the samples? The next question was, can we somehow avoid radiation damage? Is necessary to cool samples? So some people were doubting if this is necessary. And I was thinking that it's necessary, but it was needed to be tested. And finally, also, the big question of, are dynamical effects a problem or an advantage? So that we started first in Tokyo, then in Isenburg, and finally here in my institute with our own device to try to answer these questions, making different tests. So in the picture, you can see the Synergy-ED and some images of the moments where we're collecting data. And I want to focus but on sample preparation. Sample preparation is quite easy. So normally you use grids of different types and just have to deposit some of the sample on it. This grid, for example, is not well prepared. There's too much sample on it. So in general, the amount of sample which you need, you cannot see it with your eyes. And you just mount this sample with the grid inside the system. And then is where you start to look for crystals and measure them one by one, so that you have, let's say, also on the electron diffraction system, an image of the same grid where you can localize crystals and you start to measure them and to get, let's say, diffraction patterns. Important point is, and we have this system here in Tarragona, is to cool down crystals, and for this we use a geo cryo system. In this case, you can put the sample at room temperature inside the system and then cool down up to 90 or 100 Kelvin using liquid nitrogen. Also, we have another device, which is from the company Gatan, which is the ELSA. ELSA allows additionally to measure at 100 Kelvin to cryo prepare the sample. So you have a protected head where the grid comes, and you can introduce this in liquid nitrogen so that you put the sample inside liquid nitrogen and then measure in the system with the sample. So let's say when you introduce a sample, it's already cooled to 100 Kelvin, and then can, let's say, immediately start to measure at these temperatures so that you avoid a vacuum and higher temperatures when you do a measurement. And then, so to answer this question, we stood few points and started, let's say, to do different works and related to the solid state of pharmaceutical compounds. So first of all, we checked and thought how we could monitor a co-crystal screening, a co-crystal crystallization screening, when we have additionally the 3D-ED available. We also decided to investigate hydrogen bonds in co-crystals and salts, not only using X-rays and neutrons, but also using electrons as diffraction source. We also tested how it works when we have pre-labeled hydrates or pharmaceutical compounds in relation to vacuum. We checked also highly sensitive samples in relation to radiation damage. And finally, one very important point, we were using dynamical effects and dynamical processes to determine the absolute configuration of chiral compounds. And so I will show examples of all these different points during my presentation. And first of all, so that repeat again that I used for all the experiments on XtaLAB Synergy-ED from Rigaku, and I got at the beginning, because I didn't have own device, the help of the people in Tokyo, Akihito Yamano, Shuito, Robert, and then also from Germany in Isenburg, from Christian Goeb, and finally some of the measurements were performed by myself in Tarragona. And for all this processing, I use Chrysalis Pro from Rigaku, but also for the dynamical refinements, I use PETS2 and Jana 2006 and 2020. And so now going to the first example, in which we think how we could integrate 3D-ED in a crystallization screening. So in our solid state unit, we do different works related to crystallization, where we are making, let's say, polymorphism screenings, salt screenings, co-crystal screenings, and also we are doing crystallizations, for example, for separate chiral molecules. We are doing crystallizations also for getting single crystals, or also scale-ups of pharmaceutical compounds. And so I want to show how useful 3D-ED in these processes can be. So, for example, when we try to make a new solid, a new crystalline phase of a pharmaceutical compound, which should be suitable to go into the market, we have to do several processes. We start with the polymorphism screening and trying to get, let's say, a suitable solid which has the good properties. If not, we try to do salt screening. If not, we try to do co-crystal screenings. And in any case, if we do a polymorphism screening, which is itself a polymer screen, but also if we do a salt screen or a co-crystal screen, we need to do a polymorphism screening to find finally, let's say, the suitable form of this compound. If nothing works, we would finally try to get, let's say, a metastable amorphous form of the compound. And so if we do this, for example, in a co-crystal screening, we prepare our active pharmaceutical ingredient and mix it with different coformers, which will be possible molecules which could form a co-crystal. We mix them and we prepare different solutions and make different crystallizations, and finally try to characterize the obtained compound. When we do this, we do different experiments like slurry experiments, crystallizations from different conditions. Also, we do melting experiments, grinding experiments, and in these processes, so we do different steps. So initially, of course, we characterize the starting product and the coformers with the different analytical methods which are available, especially powder diffraction and Raman spectroscopy, and then we start with a massive generation of solids. Then we try to characterize them by powder diffraction and NMR and try to make a selection or classification of them. If we have different phases, then we try to characterize them more properly, and finally we go to a final solid selection. And then we would do, let's say, a scale up, and we would do a final characterization with single crystal, which implies that we need to crystallize and get the single crystals. But now the big change is that we can, in fact, erase this point and go directly when we try to do the classification and do 3D-ED and get much more information of our solids. And when we do this, so this was the end of the process where we try to get, let's say, the optimum solid. And this is an example of this process. So we took active pharmaceutical ingredient, we want to do a co-crystal of it, and we do around 800 crystallizations using all these methods and using 6 different solvents. We obtained in this process 211 solids, which were characterized by powder, diffraction, and NMR. And from this, we discovered 9 different solid phases. From them, 6 were co-crystals, 2 were solvates, and 1 was an hydrate. And we normally would characterize by single crystal, powder, Raman, infrared, and thermogrammetric analysis, and DSC. So TGA and DSC. But now we can input a new step. And instead, let's say, of doing powder diffraction, and powder diffraction is important because you always will need crystalline material to do in 3D-ED, but once you did the powder diffraction, we can do directly 3D and get information of the solid structural information. So in this screening, for example, what we did is we characterized the first solid. I think it was solid number 2, and just making one measurement with our system. This was because we had high symmetry, so we have a cubic system. We could find out from our APA. I cannot show the full molecule as you show a fragment because I cannot show it, it's confidential. But you can see that this active pharmaceutical ingredient did a co-crystal with ephenylurea. And only with one measurement, which took a minute. I mean, this sounds very easy, but of course we need a lot of preparation because we measured at a low temperature. So we cryopreparated the sample and we collected But in this case, since it was cubic, we had only to collect one crystal and we got the structure solved. After this, we simulated the powder diffraction compared with the bulk of the solid, so it's the same, so that we could quite easily characterize this compound as a crystal. In the second step, we did a second measurement of another solid. There's a mistake. This should be solid 4, I think, and then we got another structure. In this case, this APA was forming a solvate, so you have 2 molecules of paracresol in the crystal. In this case, we were needing to measure 5 crystals. We measured 2 crystals and got this data set with a completeness of, let's say, 94.3%. As you can see, error values of 50% are quite normal. This is a good error value in my opinion, so that you need to get used to these values. Okay, with this, I finished this point 1, which would be introducing the methodology of 3D-ED inside of, let's say, screenings and crystallization screenings. And now I change to another system, which is a study about a system which we, let's say, were working on it the last years. We are having a system formed by naproxen and tramadol. So naproxen is a non-steroidal anti-inflammatory drug, and the tramadol is an opioid pain medication with effects on brain and spinal cord. So that what we do is try to combine these 2 different molecules in one solid and use the synergy of being together to have a better use or a better effects than having them by separated. And so when you join these 2 molecules and try to crystallize them, if you take, these are chiral molecules, if you take the racemate of tramadol and S-naproxen, you get a chiral salt of this compound, which is plus tramadol and S-naproxen. If you use minus tramadol and S-naproxen, you get a chiral co-crystal with a ratio of 1 to 2, a chiral co-crystal of a salt. And finally, if you mix everything together and crystallize, you get a conglomerate with salts of plus tramadol, S-naproxen, and minus tramadol, R-naproxen. So you see, it's a quite curious system doing quite strange things. So that we decided to study a bit more about these solids. And I was trying by different methodologies. So we were using solution crystallization, but also melting, using a CO2 laser on a diffractometer and making in situ crystallizations. Maybe you can see here. So we fill a capillary with a melt of the solid. We add some seeds. We add some catalytic amounts of isopropanol, and then heating and warming with a control laser, we grow large crystals inside the capillary, so that after breaking the capillary, we can get large single crystals. Taking one of these large single crystals with X-ray diffraction, we could measure a high resolution data set. So we measured up to 0.39 angstroms of resolution. This is an extremely high resolution. You can see here 2 images giving you the full resolution. And we did this on a rotating anode from Rigaku, having a Pilatus detector and a micromatch rotating anode with MOLY radiation. From this data set, of course, we obtained extremely high parameter to ratio. It was 100 to 1, and a very good statistics. So our values around 2 or 3%. And so that we could do with this, let's say, a structural study using charge density, so that we could get, let's say, statistic deformation density maps of, for example, this hydrogen bond. In comparison to this, and to let's say analyze a bit better the different hydrogen bridges which we have here. Here is one, but also there we have hydrogen bonds and contacts. We try to make a study of this and understand when do we have a good crystal and when do we have a solid. So that we also did a neutron radiation study. In this case, you can see in the image, we have huge crystals. These are some, let's say, they are close to centimeter range. Huge crystals which are needed for making these measurements. We did a project in a collaboration with Laura Cañadillas Delgado in Grenoble at the ELL. And so we could measure this same molecule using neutron radiation. And so you can see, in this case, you can refine anisotropically the hydrogen atoms and can get very precise distance of the hydrogen atoms. But of course, as you can see, a big problem to making these experiments is that you need huge crystals, and this is not possible for each sample you have available. So that we decided also to see how useful could be electron diffraction on this system, and we measured in Neu-Isenburg some crystals of this compound, getting quite nice resolution of 0.6 angstroms and a temperature of around 100 Kelvin. And here you can see the crystal, one of the crystals we measured, and also the diffraction pattern. In this case, after merging 3 crystals, we could get the same structure, of course, with a good parameter to ratio, to reflection ratio. And in this case, we are having an R value of 16%, which is, I think, quite good. And we could then do a test. So we took this structure, deleted all the hydrogen atoms, and just refined the structure without hydrogen atoms. And as you can see here, all the, let's say, Fourier peaks, all the rest electron densities which appear corresponded to the positions of the hydrogen bonds, of the hydrogen atoms, including the hydrogen atom, the hydrogen bond. So that it's clear that using electron diffraction, you can better localize hydrogen atoms than using X-ray diffraction. By comparing the distances, for example, of this hydrogen bond, you could see, as expected, that at X-rays, the distance was more shortened than expected. Using neutron radiation, this should be the correct distance of the hydrogen bond to the carbon, to the nitrogen atom. And finally, with 3D-ED, we got a bit more elongated distances, but let's say quite close to the neutron diffraction experiments. Of course, we have a high standard deviation, and I need to work a bit more on the structures, but I mean, it was quite promising, the fact that you could localize directly most of the hydrogen atoms just from the electron density or the remaining electron density. The same story we did also with the co-crystal. In this case, we had 2 molecules as naproxen and 3 of tramadol, and in this case, we weren't able to get high resolution data from these crystals because they were not growing large enough, so that we could also not determine the absolute configuration, which was one of the goals of the system, because the data were not good enough. Of course, it wasn't possible to get crystals for the neutron radiation, but again, we were able to measure with electron diffraction. And as you can see, I go back to here, we have a cell which is, let's say, 9.5, 40, and 10 angstroms, and you can here recognize quite nicely the long axis, which is showing these quite close appearing reflections. And so after measuring this sample, we measured the data set of 4 crystals, and we could get, let's say, a suitable data set with, let's say, also distances which corresponded to the expected distances for these atoms and hydrogen bonds. And one important point, which will follow later, apart of getting, let's say, the structure quite easily using cryopreparation and the 3D-ED system, there's one point which I will explain later, which is related to absolute structure of this molecule. So now going to point 3, radiation damage on pharmaceutical, let's say, co-crystals. We had a system crystallized with succinic acid, which we could see. We never got the structure by X-rays. We were only having very, very small crystals because this was formed by crystallization reaction. And when we mounted this at room temperature on the 3D-ED system in Tokyo, we saw that the crystals survived only 10 or 12 seconds. After this, they stopped completely to diffract. What we did is we collected several crystals. So we collected 12 different crystals of this sample and finally merged 5 data sets of the crystals. And we were able to solve the structure and get, let's say, a structure solution which was making sense. So we could see the succinic acid, we could see the molecule which was forming this core crystal, which is also cutted, and we could also recognize where possible hydrogen bonds and contacts were, not because of the position of the hydrogen atoms, but because of the distance we observed between, let's say, oxygen atoms and carbon atoms or nitrogen atoms. Of course, here the error value is quite high. We have an error value of 19%, which sounds terrible if you think an X trace. But let's say this seems to be quite acceptable in this case for me, because we didn't get any other way to see the structure. Later on, we tried also to measure the same sample at 100 Kelvin, and although the damage by radiation cannot be avoided, these crystals were surviving a bit longer, 20 seconds maybe. But there was another point which was important. At 100 Kelvin, the crystals diffracted much more stronger, so that we were able to collect better data set, so that we have also better statistics of this. They are not in this presentation, better statistics of the structure using, let's say, low temperature. And now going to hydrates and solvates. I took one example which was patented here at ICIQ, which is the structure of the lettermobile sodium trihydrate. This is an antiviral drug for the treatment of cytomegalovirus infections, and is considered by the FDA as a first-in-class medication. So we were knowing that this is a trihydrate, so we wanted to test how this system, let's say, feels or what does under, let's say, vacuum and electron radiation. And so first we started room temperature measurement, and we didn't see any diffraction. So the crystals were destroyed by the vacuum and at room temperature. But if we started to measure and cryopreparate it at minus 184 degrees Celsius, or at around 100 Kelvin or 90 Kelvin, we could see really nice diffraction up to resolutions of 0.75 angstroms. So here you see this is the ELSA preparation tool. There's liquid nitrogen, so we prepared the crystal in the head of the holder inside liquid nitrogen and mounted. Then, so here is the grid prepared to be introduced in liquid nitrogen, so that we were able then to measure, and we could get, let's say, excellent data set of this compound using only one crystal. And the reason was because we had again high, let's say, high symmetry. It was a hexagonal cell or a trigonal cell, F3, and we could get a completeness of 73%, an error value of 13, or let's say 14%, and a good ratio to reflections to parameters. And of course, we could localize the water molecules so that we could characterize this hydrate without problems using cryopreparation. I have a second example in relation to this. In this case, we are speaking about erythromycin. Erythromycin is a dehydrate, and here you can see the TGA and the DSC of this compound. And what you can see here is that it seems that the first water molecule leaves easily the molecule, and only the second water molecule goes with more difficulties, until finally we have melting or decomposition. So that we probably have here a dehydrate. In this area we have a monohydrate. Here we have a non-hydrated form, and here finally we have the melting. This powder diffraction corresponds to the dehydrate. So that this, let's say, quite labile dehydrate should be difficult to measure if the conditions are, let's say, not the correct ones. From this system, we took also variable powder diffraction patterns. So we measured phase 1, phase 2, phase 3, doing powder diffraction with variable temperature until it melted, and then we saw it didn't recrystallize. But what we were interested was to see how much crystalline phases. And so we focalized on obtaining phase 1 of this sample of this antibioticum, which is called erythromycin, in our 3D-ED system. And we did a quick experiment. Just the morning, we prepared the ELSA, we mounted the crystals, and we measured 3 crystals, and the 3rd crystal diffracted, and we could solve the structure. This is this small crystal here, you can see. So this is around, let's say, in the big size, around 300 nanometers. In the thinner side, it was probably like 20 or 30 nanometers. And we could get a structure which was not excellent, a value of 70, 80%, but we could clearly recognize that it was a dehydrate, 2 water molecules, and this was the molecule of the compound. I didn't show the ellipsoids because they were looking really awful. But anyway, so if we simulated from the structure the powder diffraction pattern of this phase, it corresponded exactly to the one we expected to be the dehydrate. So that again, in a quite easy, quick experiment in a morning, without doing any crystallization. In fact, I was breaking the crystals to get them smaller. We could get an answer to our question and the structure solved of the dehydrate. Okay, and then going to our last part or last example, this is example of part 5, which is related to absolute structure determination using 3D-ED. So we know since the 50s and the 60s that chirality is very important when we are talking about pharmaceuticals, so that several cases which happens in this time, like this thalidomide, which generated some teratogen effects on human babies. So we could see that chirality affected strongly. So, for example, in this molecule, the thalidomide was doing the perfect effects what they expected. It was sedative for pregnant women, but in the case of XtaLAB, this was teratogen, so that when you were selling both molecules together without thinking that it's necessary to separate them, you have a problem. You had a big problem, and this happened to a pharmaceutical company, and they're still now fighting with these problems. So that, in fact, all these stories and things which happened in the past bring out that it's very important to know the pharmacology and pharmacokinetics of both enantiomers, active pharmaceutical ingredients, when we are speaking, of course, of chiral molecules, and the FDA and other entities like the European entities say that we need sensitive analytical methods to be safe and sure which chiral form we have, and that we need to do also a proper separation of them so that it's possible to make, let's say, clinical investigations, and we need to be able to compare and check the safety of racemates and its separated enantiomers. And this bringing me back to my story. So I was several years leading a X-ray diffraction lab and a solid state lab at the pharmaceutical company Bayer in Germany. And so at this time, one of the first questions I had was to find out the absolute configuration of a chiral molecule, which was a pharmaceutical ingredient. And once I delivered it to my boss, the first results, he said to me, "But is this validated? How I know that is correct? Let's imagine you give me the wrong chirality and we have same problem that is thalidomide molecule." So that after making a reflection about this, we started to make a validation. And I validated, you don't need to see any number here, it's just to show you that to validate it, we validated the absolute structure determination or chirality determination of pharmaceutical compounds, making several measurements of non-chiral molecules using molybdenum and determining the Flag parameter of this, which is the parameter which gives you the correct information about the correct chirality. And we did also the same using copper radiation. We measured several crystals and samples until we were sure that we had a validated method using our devices so that we could, let's say, without any bad thinking, give a result to our customers. And you can see that our first molecule, always in this screening or in this test, was one of the smallest molecules available in the amino acids, which is alanine. And we were able to get the proper absolute configuration of this molecule although it doesn't have heavy atoms and it's a very small molecule. Let's say this is one of the most problematic ones, yeah? Also threonine. And so we went up to bigger molecules, up to, let's say, big sugars. And then now the question is, can we do absolute configuration determination using 3D-ED? And is it somehow validated? And so we took our L-alanine and went through our system, cryopreparated, and did some measurements. First, we measured the room temperature, and then we get, let's say, a good data set at room temperature with a low resolution 0.99 angstroms. By cooling down several similar systems using the Geol cryo system, we got excellent diffraction patterns. So up to resolutions of 0.49, so we can still see reflections here at the outer border of the diffraction image, and collect data sets. So one first point then is we determine the unit cell and check how precise our unit cell determination were, and we were really surprised. So one of the maybe points which some people say is that the angles and values of the unit cell are not so precise using to be quite well corrected and seems to be working very well. And so we could also easily find the space group, which is quite a space group, and we got the results. So these are, let's say, the so-called canonical refinements of the data, and you can see from alanine, from one crystal, we could solve the structure with a good parameter to reflections ratio and an R1 value of 17%, which is still okay. After merging six crystals, this was having only a completeness of 80%. After merging 6 crystals, we got a completeness of 100%. And then a next step came in. We started to make dynamical refinements on both data sets at room temperature and at 100 Kelvin. And what we could see is that just refining the initial structure model in inverted configurations in the program for dynamical refinement, we could see a huge difference in the R values. So this is not a finalized structure refinement, just an initial refinement of the data set. Of course, if you finalize the data set to a proper refinement, for example, this crystal here was refined dynamically, and we went down to an R value of 11%, which is quite nice. But the important point is that the big difference in the R value was showing us always which one of them was the correct absolute configuration. So that in this case, we don't need a flat parameter. In this case, the differences are coming from the so-called dynamical effects, which are much stronger than the anomalous dispersion effects on X-rays. So you can see that we at room temperature, at low temperature, and using just the starting structure model, we could always distinguish the correct chiral form. We did this on several molecules, threonine, sugar, so we are still doing this measurement right now, so that I want to have soon a validated series of molecules measured in our system, so that I can be always be quite relaxed when I did a result. But we also did the dynamical refinement on all these chiral molecules I showed before. And so you can see here in this salt from tramadol and esnaproxen, we could see the absolute configuration correctly and with a huge difference in the R values. Also in this molecule where we were not able to get absolute structure determination, could get it with a very big difference using dynamical refinement. See, the difference is close to 8% in WRL value. So that this would be my last example and last explanation of all these compounds and molecules. And now let's see what our results say. So vacuum problems, I think, can be completely or maybe close to completely avoided by cooling to 100 Kelvin. radiation damage cannot be directly avoided, but we can merge data sets and collect short crystal series. We can cool the sample and get, let's say, a bit longer survival of the crystals. And third point, we can cool the samples and increase the reflection intensity so we can collect more data. Finally, data resolution is increased significantly by cooling down the crystals. So this is a clear answer to the question, is it necessary to cool down? And finally, in most of the cases, hydrogen atoms can be localized in the structure quite easily. So that, in my opinion, there seems to be no limit to the type of crystalline samples we can measure. And I was myself always surprised how good it works and how good the results are coming out using this methodology. And I have nothing more else to thank my team at ICIQ, my boss, Eduardo Escudero, my colleagues, Gisela and Marta, Rigaku's team, Ito-san, Yamano-san, Robert, Christian, Matthias, my Crisforma's team, the people doing the pharmaceuticals, Jordi, Theron, Jesus, Alejandro, and also I want to thank especially to Paul Kla, who helped me with all the dynamical refinements. And of course, I have to acknowledge also to our agency who paid for the system and referred to our, let's say, financial people. And I thank you all for listening.
Jordi, thank you for a fascinating talk. We have one question in the queue. The question comes from Salah and asks, is it possible to use this technique for 2D materials such as graphene?
Sorry, I lost your voice in between, so I couldn't hear your question.
Is it possible to use this technique for 2D materials such as graphene?
I don't really know. So we have the system quite new. So we have just the system since 4 weeks, and we don't know. But I think it should be possible. We maybe only need to try it and see if we can prepare it and measure it. So in fact, there are two conditions. It should be crystalline, with no crystals, no measurement. And they should be in the size of 20, 30, 40, 50 nanometers.
Thank you. Christopher asks, how much does the reduced completeness and redundancy affect confidence in the results?
I can't hear you properly.
How much does the reduced completeness and redundancy affect confidence in the results?
No, I couldn't hear you, sorry. I only hear the half of the sentence all the time.
Okay, let me try changing the microphone. Let's try this one. How much does the reduced completeness and redundancy affect confidence in the results?
I mean, I think we don't have a reduced completeness of data or redundancy because we can merge so much crystals as necessary to get enough redundancy and completeness. But it's true that, for example, I just had a triclinic case in P1. It were plates, and you have to work it out. I couldn't get above 80% of completeness, but we tried different grids, different ways to prepare, and finally we could get the completeness and get a better data set. But I mean, we may not have a data set like in X-rays, but I always have the feeling that the structures are correct. They look great. If you delete them, the atoms appear where they should be. Hydrogen atoms appear where they should be. And for me, it's a miracle. So you're measuring the crystals of few nanometers and you get the structure, you get the data set. And I think now we have to learn in the future how I can answer your question. I don't know it. So we have to learn and see. Yeah.
So Pierre asks, have you experienced with variable temperatures on some of the compounds yet as the Catan cryoholder is able to control?
Sorry, again, I can't hear you, sorry.
All right, let me try this. So have you experienced with variable temperatures on some of the compounds yet as the Catan cryoholder is able to also control temperature? So in other words, have you tried variable temperature experiments?
I tried, I don't know if I hear correctly your question. So I tried to measure with Agata and ELSA in different conditions. Normally, I prepare a sample at 100 Kelvin and mount it at 100 Kelvin. But in several cases, or not in several, because I didn't have so much cases, but in some of the cases, I had trouble, for example, with ice formation, or, for example, that my sample somehow changed. I don't know if there was humidity, which froze and then destroyed the crystals. And then I find a way, I got a good hint from one of your people at Rigaku, so that I mounted the crystals at 170 Kelvin, mounted it at 170 Kelvin. This was then helping all the water in the system to sublime. And then cooling down to 100 Kelvin, I got excellent data sets and very clean, nice crystals of samples, which initially were expected to be very sensitive. I don't know if I answered to your question, sorry.
I think that's a partial answer. Thank you. Simon asks, ED can readily distinguish between and locate light atoms. Do you have much experience of successfully doing this in heteroatom structures? And do you think you would be able to successfully refine hydrogen atoms anisotropically?
To the first question, I have not so much experience. I hope I will get it soon. I don't forget, I just have the system been working for 4 weeks or 5 weeks, and I was able already to show a lot of structures, but we couldn't focus on all the fields. It's true that it's sometimes difficult to distinguish between atom types, and I don't know. We need to see what the future says. I have to measure more samples and test. I don't know. I cannot answer this. And in relation to anisotropic refinement of hydrogen atoms, I'm not really sure if this is necessary to make sense. What I see is that I can detect them easily. I can find them easily from the structure, and I can find the position, but still do not have so much experience, for example, in what's happening when I have a disorder. Unluckily or luckily, I didn't have disorder in my molecules, so that I couldn't check how, let's say, for example, disordered hydrogen atoms behave. And so for me, the point was to localize them and know at which distance they are. I don't know if it's necessary, or I would refine them anisotropically, but I didn't try it.
Thank you. All right. Sophiane asks, the data collection time is approximately 1 minute. What is the sample preparation time for both room temperature and low temperature from picking the vial until it is inside the diffractometer and ready to measure?
Yeah, I mean, 1 minute measurement sounds like very quick, but in fact, when I work in a project, yeah, I was working in a difficult project last week, for example, with a sample which I had to find out the absolute configuration, it was having low symmetry. And so when I started in the morning, I have to prepare the device and take an hour until it's fit for starting the measurement. At the same time, I start to cool the ELSA down so that it takes, including this time, maybe half an hour more. Then I have it, let's say, at 170 or 100 Kelvin. Then I mount the sample, go into the device and start measuring. And I don't measure 1 minute, because maybe in the first day I measured like 40 or 50 crystals until I was having a feeling I could solve it. And so that finally, for this difficult project with low symmetry, I spent 3 or 4 days measuring, doing 1 minute measurement, but doing several of them. Maybe I did 150 or 200 measurements in these days. And what was nice was that with the ELSA, you can mount the crystals, but if you hold the cryo preparation set cooled down, you can go back to it, mount a new crystal, and go in without waiting, so that I was able, let's say, to make 5 experiments one by one, following without interruption, so that I spent all day measuring different samples, or let's say the same sample, but different grids of the same, just by mounting and demounting the ELSA, so that only lost the time in the morning preparing everything. Then additionally, you have to let the ELSA overnight on the vacuum and preparing it properly, making the heatings and all the processes during the weekend, so that it's always in the best conditions, so that you don't have, let's say, icing or losing temperature and all these problems. Yeah.
Thank you. So as the host, I'll take advantage of this and ask the last question.
Yeah,
Considering your pipeline before you received the Synergy-ED and considering it now, how much more throughput do you think you'll be able to achieve in any given time interval?
I think it's not a question of throughput, because I don't stop to do X-rays. I have a high throughput, so we measure between 400 and 1,000 crystals a year in our X-ray, single crystal X-rays. And we are focusing on different samples now. So we are focusing on non-crystallized, so samples which do not have crystals, samples which are different because they have problems, samples which are chiral, and sometimes, let's say, for example, this erythromycin molecule, which I did the structure determination for the dehydrate, I spent 2 or 3 hours in one morning. Yeah. In other cases, I spent a full week. And in other case, which was a metal complex, I spent at room temperature, maybe I spent 1 hour and I had the structure solved. Yeah? But there is one point for me which is important. It's a time-demanding method, because when I do single crystal with the X-rays, I go there, mount the crystal, go for a coffee, then I solve I look for the cell and I refine the structure. So it's a routine, a time routine, which allows me to do it. When I am sitting on the ED system, it's like hell. I measure crystal after crystal. I getting a lot of data sets. I have to process all these data sets. I have to see which is the correct one, which are the correct cells, which that I can merge, so that you cannot go. I spend hours and hours in the lab and look at the clock. Wow, it's time to go home and it's late, and it demands you a lot of time, so that you work a lot of hours because you cannot go and you have to process all this data. You get a bunch of data, but don't forget, you get solved problems and things which maybe you were not able to solve before. So it's not a question of pipelines, it's a question, can I get something which I wasn't able to get before? Yeah.
So it's enabling technology.
Yeah.
Thank you, Jordi. So let's all give Jordi a round of applause for the presentation. I'm not sure I can see how I can do this since it's a webinar. So thank you very much, Jordi.
Yeah, thank you.
As I said earlier, the presentation will be available as a recording shortly at the link provided earlier. Thank you, Jordi. Have a good day. Everybody else,
thank you.
have a good day.
Bye-bye.
Bye.
Bye.